Okay, so here we go with inductance and time constants. So inductors cause a bit of a problem. When we deal with time constants, we're looking at unit 14 here. So here's something in concept just for you to think about. The effects of inductors and how they push back on circuits. So a lot of things in the atomic world are relative in some way to the physical world we know. So here's a couple just ideas in concept, and I can't stress that enough. This is just to like a little thought experiment here. So say this is a water tap, and we've paralleled off here, and we have two hoses. This hose has a splice in it and a reduction in size, which would be considered a resistor. This hose has been coiled around. Now both these hoses would be the same length here. Now say this is a drum of some sort or whatever, this would be coiled around. And what you're looking at here is we deal with the term angle 90 degrees. And if you look at it, it's physically 90 degrees out of phase right here. So as this coil is approaching, it's in a straight line, and then all of a sudden it gets wrapped around, and you literally have a 90 degree shift just in the physical sense. So picture yourself running in a straight line. You're just running as fast as you can. Now you can try this at home if you like and go into whatever the open area is. I suggest you give yourself a little bit of room. Don't do this on a street. But just run in a straight line. You're going to find it's going to be just like it always has been in your entire life. But if you decide now to run and then start spinning around as you're running, you're going to find that you're not going to be able to cover the same amount of distance over the same amount of time. Because this momentum, this orbital momentum here, is going to cause a problem for how you progress. So you can consider this as running through a straight line and just sort of squeezing yourself through a tight portion. And then this you can consider as you're running down the straight line, then all of a sudden you got to start turning. Well, it stands to reason then, if you got to just squeeze through, it's going to take maybe a little less time, but you can get through. So it stands to reason that you're going to get to this point a little quicker than you're going to get to this point. Now, when we talk about the amount of time, it's really just a fraction of a second as far as the inductor is concerned. But the whole idea here is that it takes longer because the inductor, the way it reacts, the motion, and more to the point, the magnetic field that it creates. So there's a couple videos to watch, and this is all sort of relative to those videos. So now, if this was a soft, pliable sort of rubber, nothing too rigid, one of the things you may find here is that as it's trying to push itself through, you have this backup. It's trying to make up, and again, you're going to slow down, kind of like this. So what you're going to have here is a swelling. It's trying to get through, but it can't. So this, now what you have is a backlog right here. And you have what would be a little eddy current building up in here as it's pushing through. And then when it pushes through and everything starts flowing again, this will then back off, relax itself, and then you have a steady flow running through the circuit again. But upon energizing it, it's going to want to push itself through, and it's just going to have a bit of a problem getting through, which is going to create a problem right in here. So this is another, again, this is in concept, it's just a thought. But that's sort of the idea of it's going to take a little bit longer to get through because of the resistance that's in here, either a magnetic field, the physical winding. and whatever it may be. So when we use inductors, if we go back to the inductance video, we have Eli the Iceman, and the voltage leads the current. That's the language that we use for this kind of circuit. So if we look at that, so when we talk about voltage leading current, we end up with an image that's sort of like this. So now the voltage can lead depending on the circuit, but this is just for the sake of it. So the voltage leads the current. It leads the current in time, is sort of what it's saying. But if you look at it this way, it says it leads the current, but it's also behind the current. Now again, this, I can't stress this enough, this is just thinking about it. So it leads the current in time. So if we go back to here, the voltage and current, the pressure and the flow, when it hits the inductor, is occurring at the same time. They're flowing together. It hits this coil. Now it swells up in here, and you have this eddy current going on here. It flows, it flows, it flows, it flows, it flows. But now, so it trickles out, you have current, but you still have this back pressure in here until it relaxes. And maybe one way to think about this is that it is now pushing the current that has flowed out here. When this stabilizes and everything starts to travel through the inductor as it wants to, it is now pushing all of this, everything that trickled out here ahead of when this started becoming bulbous. Everything started coming out. That's fine. But as soon as this gets back to its relaxed state, you have the pressure that's pushing all of the everything from on the front. It's pushing it from the back now, because this had to get caught up. So you have this buildup here. It's got this pressure building up in here. It comes through, and then when it stabilizes, the pressure that's pushing everything is coming from the back. It's pushing all of the, if this was water, all of the water trickled out, it trickled out, it trickled out. This is bulbous, it's staying that way. Then it's all filling up here. This returns to its relaxed state, and at that point, it's pushing all the water ahead of it. It's pushing it from the back. So voltage leading current in this manner. I'm not saying that's exactly what it is, but again, just a thought experiment to get everybody sort of thinking about what one means. And again, do the research, check it out, see what other scientists have to say. But basically, the voltage leading the current is the standard. This representation is what you're going to find. And that's it for now.